Hello, everybody. Thank you for joining us today. So, we're picking up where we left off yesterday in the section in Vakil on sheaves on a base. Um, so, we had ended with kind of this fact that taking the stock of a sheaf of abelian groups is an exact functor. And now we have kind of a bunch of similar theorems about left exactness. um, of the section functor, and then the push forward, and then hom, and then we're gonna kind of jump over stuff for OX modules. You'll have to forgive. It's 6 in the morning. We decided to hold it early, and it's technically my fault. But that means I'm gonna be running a little slower than usual. Um, we're hoping to get through that and the inverse image sheaf and finish out chapter 2 today. So hopefully in the next hour and 40 minutes. So without further ado, let's do it. So, okay, there we go. So let U be open X, and 0 into script F into script G into H. Um, is an exact sequence of abelian groups of sheaves of abelian groups. Sorry, my apologies. Um, show that U into or that 0 into F over U into G over U into H over U is exact. Um, and so here it's important to note that we're really seeing kind of like the sections. Um, so if we have alpha, beta, and gamma, we want to show that it's exact at f of u and g of u. Um, and so then, and this is really getting mapped. Let me. This is getting mapped by gamma, the global sections functor.
Mm-hmm.
So that's really kind of what we're doing here. And so we're given, I guess we'll make this alpha prime, beta prime, gamma prime. We'll make this alpha, beta, and gamma with cur beta equals m alpha, cur gamma equals m beta. Um, and so what we want to do is we want to let let a let f and f such that beta of f equals 0 in G. Um, Fn m alpha, then the global sections functor on f over u is equal to f restricted to u and f over u. Um, but f restrict u is in m alpha and beta prime in the global sections functor on beta comma u is equal to the restriction map of beta to u. So f restricted to u, beta of f restricted to u is equal to 0 in g of u. And cur beta prime is equal to m alpha. So is exact at f of u. Similar logic goes for g of u. And then there's kind of this important plot point. So similar logic was for G of U. Now consider the same diagram except we go into 0 by theta and theta prime. Um, if this is A dot and this is B dot, so essentially if alpha bullet is exact, B bullet need not be. And so um, the idea here is if we let exactness will break at h, so let cur theta equal m gamma, um, then m gamma is equal to h, um, since theta goes from h to 0. Um, then f in the global sections function, or then f in h has theta of f equals 0, um, with g and g such that gamma of g is equal to f, but gamma of g over u is equal to gamma of g restricted to u, which is equal to f restricted to u in h over u. Um, let theta prime be gamma of theta over u. Um, if f restricted to u um, is constant, um, and non-zero. And no, it has to be non-constant. And is that clear why?
No.
Okay, consider the integral of x squared,
Hmm.
but consider it visually.
Yeah.
So we have our parabola, and if we shade in area in
Hmm.
symmetric amounts, this integrates to 0, which we can think of as evaluating to 0 over u.
Yeah.
But if u is a non-symmetric interval, like -2 to 1,
Yeah.
it's going to integrate to something non-zero. And if
Right.
we integrated it over the whole domain like we did in H, it doesn't
Okay.
have to, like it'll integrate to 0.
Yeah.
But otherwise it is non-constant and 0. Whereas if it were constant, it would be forced to be 0.
Okay.
Um, so if it is non-constant and non-zero, then f restricted to u is not 0, but theta of f of u is left undefined. So, or sorry, theta prime, curve theta prime is not equal to m gamma prime. So this doesn't have to be exact.
Okay.
Okay, that actually went a lot smoother than I was thinking it would. So, similar exercise, which is left exactness of push forward. So, let 0 into F into G into H. Um, be an exact sequence of sheaves of abelian groups on X. Um, let pi from X to Y be a continuous map. Show that 0 the push forward sheaf is exact. Um, and where did we define the push forward? Found it. Okay. Um, no, it has to be before here. Was it really before the skyscraper sheaf? No, it can't be. This is... Ah, found it. Okay. So, where pi star of f um is on y with pi star of f is equal to f of pi inverse of v, where v is an open subset in y. And so really we're restricting ourselves to open sets. So this one is kind of the obvious one, actually. Is it clear how this is the obvious one? Like, talk me through the logic.
He's kind of just going through the other one using the universal property again.
Not exactly. So it
Okay.
has more to do with it is a special like the or rather the other one is a special case of this. Um
Oh, okay.
so it's the special case where y is a point. Um whereas here, well, we know that since pi is continuous, pi inverse of an open set is some open set in X. And
Right.
so really we'll think of the push forward of F as the section over U.
Okay. Oh, okay.
But it's getting identified with a whole space, right? So these are
Yeah.
both kind of special cases of each other.
Yeah.
Um, but last time we identified the global sections functor as kind of like a point, not necessarily in Y. Um, Here we're identifying it with, the the image of pi.
Yeah. Okay, that makes sense now.
And so what this really looks like is all of the greens are gamma of pi inverse of b, right?
Hmm.
Um, and so that kind of completes it, since we're not demanding right exactness.
Yeah. Okay.
So, um, our final one is left exactness of Ham.
Okay.
Um, so let F be a sheaf of abelian groups on X. Um, Show that Ham of stuff comma F is a left exact contravariant functor ab x to ab x. So we'll start with let us be let us get sheaves like so, GHK, um with alpha beta gamma, and then we want to send these through by Ham um to, I guess, Ham GF. Suddenly realizing that I didn't give myself enough space. KF, um, which goes, this is contravariant in the first slot. Um, So these are the morphisms from G opposite to F. These are the morphisms from H opposite to F. And K op to F. Um, and then we'll call this alpha prime, beta prime, gamma prime. And so we'll let F be in G, or F be in M alpha. M alpha such that beta of F is 0. It's worth noting M alpha is equal to G. So beta of F is 0. So G is exact. And then um, of F to script F um, is a stalk mapping F op from H back to G. Um, and so F op by F prime. And it's not from H back to G, it's from F back to G. No, it is from H back to G. H to G. And then we're mapping this F prime gets sent into the sheaf of abelian groups by all of the functors F such that F is in. So preserves functions with right inverses, which is equivalent to surjectivity. Um, and
Tim, can you give me
then,
1 second?
yeah.
Sorry, my parents were putting on coffee, so I just wanted to ask if they could make me one.
You're good. I understand. But yeah, so Helm preserves functions
Yeah.
which are surjective. And so then f prime, no, so f associated to f prime has beta prime of f equal to L in H op script f by f prime getting mapped to hom 0. So f is the zero functor to script f, and f is in the kernel of beta prime, but alpha prime, image of alpha prime, is equal to g, which is equal to this kernel. So is exact at hom gf. And it follows for the other ones too, with similar proofs.
Yep.
Okay. Yeah. So, conclusion of this section is that just as pre-sheaves of abelian groups on a topological space form an abelian category because all abelian categorical notions make sense open set by open set, sheaves of abelian groups on a topical space form an abelian category because all abelian categorical notions make sense stalk by stalk. Um, so the final thing that we're going to describe is called the inverse image sheaf. Um, and it is a supposedly fundamental but intricate notion. We will not need it for some time, so this may be left for a second reading if needed. Um, huh. Then in that case, maybe we leave it. I mean, we have time. Let's go for it, and if we don't finish it, then that's fine.
Sounds great.
So, section inverse image sheaf. So let pi from x to y be continuous. Script f is a sheaf on x. We have pi star f is the push forward sheaf. F of pi inverse of v, where v is open in y. There's also a notion of an inverse image sheaf. Um, Definition by adjoint. Um, Inverse image sheaf. Pi inverse is the left adjoint to pi star. Um, so to actually construct this, the pi inverse pre-sheaf g of u is the co-limit of all v containing pi of u of g of v. So we're collecting all of the g of v's which contain pi of u. And this is the inverse image sheaf. And it doesn't need to be a sheaf because it can map 2 points to 1 point. And now we can define the inverse image sheaf from this pre-sheaf as pi 1 g is equal to the sheafification functor of that pre-sheaf. So we just take all the things that do agree. And so as a theorem, pi inverse and pi star are an adjoint pair. And so this is where I really want to skip it because showing that things are adjoint pairs takes freaking forever. Like, i.e., there's a bijection. So if f is sheaf on x, g sheaf on y, then there exists a morphism in x of the inverse image sheaf to f, where this morphism class is a bijection to the set of morphisms on y from g to pi star f. And it's natural in the sense that it's functorial in both f and g, which has a long definition. Um, where is the definition? Okay. Basically, that more y. Nope, it's the other way. More x pi inverse g to f goes to more x pi inverse to g prime goes by, this is tau gf, goes by tau gf to more y of g prime pi star of f goes to more y to g pi star f. And this is tau g prime. This is tau g f, where there exists a map f from g to g prime such that commutes. And then
Oh, yeah, I mean, we're still in the class, but they said it should be wrapping up. Like they said, New Jersey pretty much got snow and more freezing rain.
Garrett, do you need me to pause for you?
No, I'm all right.
Okay.
Sorry.
Um, yeah.
Oh,
So, of course, this is the bijection that we care about,
right.
but it commutes through
Mm.
strange methods. Yeah, I don't really feel like doing that problem.
That's fair.
Vakil said that this is optional second reading, so I'm just gonna do the
Okay.
interesting stuff.
All right.
So a special case of this that will maybe make this a little more clear is that if x is a point P and y,
Mm-hmm.
then pi inverse of g is the stock GP. Um, and maps from GP to a set S correspond to maps on sheaves of Y from G to the skyscraper sheaf with S at P, such that basically I'm trying to do a script F for skyscraper, but that looks like an L, so we're gonna run with it. So it's equal to S, or if U is equal to P, otherwise. Um, as an additional theorem, so the stalks of pi inverse G are the same as stalks of G. Um, More precisely, there exists a natural isomorphism from the qth stalk to pi inverse G stalk to P. Um, so for sketch, they recommend using the colimit definition. So pi inverse G is the sheafification of the colimit. So pi inverse G at P is colim V containing pi of U such that U is in P of G of V. Um, and this is taken at P, and I don't remember what the outside brackets were for. Um, oh, and I guess I should make this Q, not P. And so then localization commutes with colimits. So this is the colim V contain pi of U, G of V localized to Q, which is the colim of G localized to Q, which has a bijection to G of Q. Does that make sense? Oh, I remember what it was. Hold on. It was the sheafification. That's important. So, does that make sense? Is that an acceptable thing, Garrett? Garrett, you there?
I'm so sorry, my microphone was muted. Yeah, that
You're
looks
good.
good. I didn't even realize.
You're all good. Ooh, an easy but useful. Oh, that's my favorite kind. Um, ah, the theorem. If U is open and Y, and I is the inclusion from U to Y,
Hmm.
um, and G is a sheaf on Y, then the inverse image sheaf to G is naturally isomorphic to the restriction map at U, and that makes a ton of sense. So I inverse G is the sheafification of the localization at Q such that Q is in U. But then that's just a bundle of stalks forming U, which is equal to G restricted to U. That is a very easy one, and
That
that is
one
also
was
very
easy,
useful.
yeah. Very intuitive.
Yeah. Um, okay, here's a less easy one.
Oh,
So theorem pi 1 is an exact functor from sheaves of abelian groups on Y to sheaves of abelian groups on X. Um, and proof is that exactness is defined on stocks. Proof summary. Exactness can be checked on stocks. Um, so we have three big definitions that I want to get through. So definition one is the push-pull map. So let W to X by beta prime alpha beta alpha prime be commutative and let script F be a sheaf on X. The push-pull map is, oh, sorry, the push-pull map beta inverse alpha star F to alpha star prime beta prime inverse F is as follows. And it's on sheaves of Y.
I see.
So start with the identity that B prime inverse F is isomorphic to B prime inverse on W. This is equivalent by adjointness to F bijecting to beta star prime beta prime inverse F on X. And then apply alpha. So alpha star F bijects to alpha star beta prime inverse F on Z. Um, so we started with beta prime inverse F is on W. Then we moved it over F bijects. So the forward and backwards movement on X. Then alpha star moves us down to Z. And then this is the map by commutativity. This is equal to alpha star F bijecting to beta star alpha prime star beta prime inverse F on Z. So beta prime inverse goes like that to alpha prime to beta star. A lot of convoluted notation, but it's just commutativity.
Yeah. Also
Um,
seems like a lot of diagram chasing.
yeah. This entire construction is functorial in F.
Okay.
Okay. All right.
All right.
So now we'll define the notion of a support. So let F be a sheaf. of ab groups on X and S be a global section of F the support of S is the set of all points in X such that the stalk at P is non-zero. So where S has a non-zero germ. We think of this subset of X as the section where S lives. The complement is the zero section. This is a closed subset of X. So theorem sub S is closed in X, meaning it's the complement of an open set. So it's all of points in X which have non-zero germs. Well, what's the complement of sub S? So sub S complement is P and X such that SP is zero in FP, so it has a zero stalk. And this is the zero section on S. Well, no, it's um this is open. I'm gonna check Math Stack Exchange. Uh so we can pick a subset of this that zeroes out. So let UI contained in sub S complement, then for every X naught in UI, S evaluated at X naught equals 0 implies that the restriction map of S at UI equals 0. So sub S complement is a union of such UIs. There we go. So it's a theorem in topology, which, again, I know you haven't taken, so don't worry too much about this.
Okay.
But it's a theorem in topology that a set is open if it's a union of a bunch of open subsets, right?
Okay. That makes sense.
Um, yeah, and so we're saying, okay, we want to show this thing is open. We're going to pick an open subset of it that's arbitrary, and then it's going to be the union of a bunch of these.
Yeah.
Um, um, Now we're going to define support of a sheaf is sub G is the set of all P and X such that the order of the stock isn't one. Oh, such that it doesn't all evaluate to one thing. Points with non-trivial stocks. Um, this is equal to the union of supports some index I. Okay, and that's everything. We finished chapter 2 of Vakil.
Awesome.
We are on to schemes next time.
Let's go.
All right, well, I'll go ahead and end the recording here. I feel pretty happy with this.
Yeah.
Um, yeah.